Hello, this is Analog Circuits 18EC42 Module 2 Lecture 3 Part 2 Frequency Response of CS Amplifier. In the last lecture, we considered the three frequency bands of the common source amplifier, and then we considered the high frequency response. We will consider now the low frequency response of the amplifier. So now in the low frequency, we have written again the equivalent circuit over here. This VCC is grounded in the analysis, in the AC analysis. So therefore, we have connected it to ground, and naturally we can see that you have ID over here and I0 over here, and this will be coming in parallel with this ID. What you call the current which is through this is getting distributed into this as well as this. So you can have a relationship between I0 and ID, or you can consider that the minus ID is flowing in the reverse direction like this. The minus ID is flowing in the reverse direction like this, and you can write an expression for the I0 in terms of ID, I0 in terms of ID, or rather I0 in terms of minus ID. Minus ID is flowing here, part of it goes to this, part of it goes to this, and then you can write the expression for that. So from the figure, you can always write Vg is equal to V sig multiplied by Rg divided by Rg plus 1 by SCC1 plus R sig. This can be got something like this. So Vg is the voltage across Rg, and V sig is over here. So V sig is getting distributed between this combination and this over here. So again, it will act like a what you call potential divider network, wherein I can just say that the current flowing like this, the current entering the MOSFET is 0. So therefore, all the current which is flowing through this will flow through this, and hence V sig divided by the what you call this total thing, the impedance due to this and impedance due to this. Impedance due to this will be R sig plus 1 by SCC1 plus the Rg will be the what you call in the denominator. If you multiply that current by means of Rg, then you will get the value of Vg. So thus we have Vg is equal to V sig divided by this total thing will give us the current in the input network, and then you multiply by Rg, you will get Vg. This can always be written as you can take out Rg divided by Rg plus R sig as common. So then it will become S divided by S plus 1 by Cc1 Rg plus R sig. Now this is a expression in the Laplace for a high frequency network with the cutoff frequency as this, S by S plus omega naught or omega p1 you can consider, and that will be the low frequency network with a corner frequency of this, and this is the corner frequency in radians per second. Omega p1 is equal to omega naught is equal to 1 by cc1 rg plus rc. It is S by S plus wp1. Then we have the ID. ID is given by Vg divided by 1 plus Gm plus 1 by SCS. And this can be considered again from the figure something like this. Now you can see that here ID is the current which is flowing through this, and you have the what you call 1 by Gm here, and the impedance due to the CS is 1 by SCS in the Laplace transform is the impedance, and this impedance due to this is 1 by Gm. So the current ID will be equal to this Vg, which is appearing across both these together. Between this point and the ground also you have Vg only, because this is the same point. This point and this point is just same. So between this and ground you have Vg. Between this and ground you have Vg. So Vg is equal to ID divided by the so to say ID divided by rather ID multiplied by the impedance of this total thing, and hence ID will be VG divided by the impedance due to this total thing, and that will be impedance due to this total thing is 1 by GM plus 1 by SCS, and that's what is mentioned over here. Vg divided by 1 by Gm plus 1 by SCS, which can be again written in the alternate form. You can just take out this Gm common, Gm Vg is common, then this will become S divided by S plus Gm Cs. So again, it is of the form S by S plus omega naught, or rather S by S plus omega P2, wherein this value will be Gm by Cs will be the omega P2. Again, this is a high pass network. S by S plus omega naught will be a high pass network. So with the again the break frequency which is there as WP2 is equal to GM by CS. Cutoff frequency or break frequency 100. Same. So you have the second frequency component which is GM by CS. Again from the figure, the output voltage V0 is given by the expression I0 by RL. So as I said initially, we have here ID, and in the reverse direction you can consider it as minus ID, and this minus ID, part of it is going to flow as I0, and part of it is going to flow here. So we can write an expression for I0 in terms of minus ID, and that will be naturally what we call again a potential divider type of the distribution of the current minus ID between I0 and the current flowing through RD, and therefore the value of I0 will be equal to minus ID into I0. I0 itself will be this value of I0 is nothing but you can always write V0 by RL, or V0 is equal to I0 into RL. V0 is equal to I0 is flowing downward, so therefore V0 is equal to I0 into RL, and that I0 can be written in terms of minus ID, and I0 will be minus ID into the what you call impedance in the opposite arm, that is RD, divided by the sum of the impedances in the two arms, minus ID into RD divided by the sum of the impedance in the two arms, and the two arms are RD plus 1 by SC2 plus RL, and all the three things, further simplification of this will lead us to the expression which is something like this. So this can be again considered as an exercise of the derivation of that from what I have told just now. You can just derive this expression very easily, So this again, you can see that it is a high pass network with the break frequency or center frequency as WP3 is equal to 1 by CC2 RD plus RL. So we can substitute the in 4.137 in this expression we have ID, and the ID value can be substituted from here, and further the VG value can be substituted from here, right, from rather here, and we will get the expression like this. So where we have 3 poles and also 3 zeros, 3 poles and 3 zeros. So this again, you can see the rest of the thing over here is again the mid-band gain. This is again the mid-band gain. So V0 by Vc is our GV, and this is the mid-band gain, and this gives us the low frequency response in terms of 3 poles. So the low frequency response will be something like this over here. Because of the 3 poles, we have 3 cutoff frequencies. So this just gives us the Bode plot or the frequency response in terms of asymptotes, which we'll study in detail in the control systems, right? Which is 18 EC43. Okay, 18EC43 we'll study more in the Bode plots, but for the present you can just consider that as, the three cutoff frequencies over here, due to which it's going to appear, and this will be the fall which appears in the low frequency region. So here we see that WP2 is the one which is there here, and WP3 is here, and WP1 is here. Okay, the order please note: WP2 is here, 3 is here, and 1 is here. So in place of W, you can say F also, because of the sole reason that F is equal to W by 2 pi. So WP2 value is the one which is more dominant, more, what you call, you can see that this is larger compared to these two. This is larger compared to these two. That's what is mentioned over here. WP2 is larger than WP3, and that is larger than WP1. So FP2 will be larger than FP3, is larger than FP1. So in that case, we see that the larger one is known as the dominant pole. The larger one is known as the dominant pole. And that, again, we'll study in the control systems 18EC43 more in detail. So this dominant pole is the one which is, has more say than the other poles. So therefore, you can consider FL as almost same as the FP2 rather than, FP3 and FP1. They might have the effect, but the effect due to this will be very small compared to this, because this corresponds to the dominant pole. That's why we can approximate FL to be equal to the FP2. So with this, we come to the end of the lecture 3, part 2.